I'd like to thank the organizer for the invitation. So the purpose of my talk is to Is it okay? Yes. Thank you. So I just wanted to visit a bit the Sine-Gordon model. So this project started. So it's a joint work with Hubert Lacouin in Rio and Vincent Vargas in École Normale Supérieure in Paris. So a few months ago, this project started when we were looking for integrability results for the quantum Toda fields, and among these fields, the most simple model is probably eventually the Sine-Gordon model. So we have tried to find in the literature some results about the integrability of the Sine-Gordon model, and we found a couple of papers. Among them, there is this crazy formula. So there is no need to understand this formula. It's just because I find it crazy that I put it on the blackboard, but there is no need to understand this formula in my talk. So we have found this formula, and actually, what we wanted to these are formula that you can find in physics paper by Zamolodchikov brothers and Faideyev and Lukyanov. So these are the only guys that can figure out such a crazy formula. And there are also some papers about 1D plasma and 2D boundary problems in the Sine-Gordon model by Fendley, Lesage, and Seller. Okay, so in the beginning, if you want to prove this formula, you have to make sense of this, of the left-hand side. And so we have tried to find in the literature how to define such expectation value in the Sine-Gordon model. And actually, we soon realized that there are not so many papers able to make sense of this correlation function in the Sine-Gordon model. So we've decided to try to do something in this model, and this is what I want to explain. I don't want to prove this formula, but rather to have a method to renormalize the correlation function in the Sine-Gordon model. Okay. So maybe let's start with the two-component plasma. So I can formulate the problem in dimension G. So you have a bounded domain, let's call it G, and in this domain you have charged particles. So the x is the position of the charge, sigma is the sign of the charge, so plus or minus 1 depending on, so you have charged particles, and I require the configuration of charges. So you take an even number of particles, and you require that the sum of all the spins of particles sum up to 0. This is why I put a 0 in the configuration of particles. So this is a neutral gas of particles, and if you are given a configuration, so this is all the position of your 2n particles together with their signs. You can define the energy of such a configuration by this sum here. So here you have a log. This is the interaction term, and you regularize the log with a scale parameter, let's call it t. So in such a way that the Euclidean norm is regularized at some scale t. Okay.
You're actually in the plane, or in, I mean, because you put arbitrary dimension up there. I mean,
it's in RG.
But I mean the Coulomb potential in RG.
Yeah, but I'm not discussing the Coulomb potential. I'm discussing the two-component plasma. Okay. So in dimension 2, of course, this is the Coulomb potential. Okay, so this is a neutral Coulomb gas in dimension 2. So let me record this term here. So the energy is just the sum. So this is the sine times the log of positions. Okay, and okay, no, it doesn't work. So maybe I should.
That's where I was back.
Okay. So now, once you've defined the energy, you can define the grand canonical partition function. So this is the sum over, as usual, you sum the exponential of the energy of each configuration, and you sum over all possible configurations with the usual normalization of the. Well, this is the grand canonical partition function, and what I'm going to do now. So you're interested in the limit when the regularization parameter goes to infinity, so that you recover the log here in the energy. Okay. So, well, there is. Let me explain what is expected from this model. So,
do you need alpha to depend on t or
no. I will discuss only the ultraviolet problem. So I won't touch here the alpha here. It's fixed. This is your question, right? Yes. So alpha is fixed. So what is expected from this partition function when the regularization parameter is set to 0 is that there is a sequence of thresholds, and the first threshold is the phase where the grand canonical partition function converges, okay, without any further operation or procedure. So it will give you a gas of isolated particles. Now there is a threshold. So for the value beta square equal to g, there is a threshold where the position, well, dipoles will be created, and you can understand what will be the contribution to the partition function. So if you look at a dipole, so a dipole it's a pair of two particles with a plus and a minus, which are basically separated by the length of the cutoff scale. Okay, so this is a formation of dipoles like that. And if you want to understand the contribution of all configurations of isolated dipoles like that, you just compute the energy of a dipole. So you take two charges with opposite sign. You compute here the energy for such a dipole. So, and you find that the energy is basically it should be minus 2t, and if there are two n particles, this will give you n dipoles, and so this is the contribution of all isolated dipoles. So if you look at the partition function, if you want to have a dipole in the grand canonical partition function, you have an integral over your domain to the power 2n, and if you have isolated dipole, this will correspond to particles which are separated by the scale, say, to the power number of dipoles. Okay, so there are n dipoles, and this will be basically this region of the space has volume exponential of minus dt to the power n. Okay, so this will be so just a simple computation tells you what is the contribution of dipoles, and so you'll see that this quantity here starts to diverge when beta square is bigger than g. Okay, so so beyond this level, you have an increasing amount of dipoles contributing to the grand canonical partition functions, and then there is another threshold where you have a contribution from quadrupoles, and you do the same trick. You compute here the energy of quadrupoles. There are n over 2 quadrupoles. This will give you the contribution of energy, and then you compute the region of the space for which you have a quadrupoles. This will give you this term here, and you can iterate this procedure. Okay, and you will see that you have a sequence of thresholds where you start to see a contribution, a non-trivial contribution from two p poles. So this is the p particles at distance of the cutoff. Okay. So so you have this sequence of threshold. At each time you cross this threshold, you have a new divergent contribution coming from two p poles, which are well, you only see these two p poles in this phase. Okay. So this is the multiple pictures, and of course you see that these thresholds converge to 2D, and at 2D there is a a transition, called a BKT transition. I won't discuss this transition in my talk, okay? But there is clearly a limiting threshold where this value accumulates, okay? So this is the general expected multiple picture of this two plasma component. And to study this model, there is a well-known tool which is called the Sine-Gordon transformation.
So are you saying that if you take a log potential in any dimension, you have this phase transition?
I'm claiming that if you are in any dimension, you have this picture of multiples, whatever dimension. Okay. And for beta square equal 2d, beyond this value, I'm not able to show that there is a free field, but it should be the case, I guess.
In any dimension?
I think.
Yeah?
Dimension appears explicitly in this formula.
I cannot prove that nor give a convincing argument for what happens beyond this value. I don't know, but it should be the same. Okay. For instance, in 1G it's clear. In 1G it's clear. 2D it's more or less proven, but beyond I don't know exactly what happens. Okay. And as I said, I won't discuss the BKT transition. Okay. So to study this model, there is a well-known transformation. You want to represent this model as a Gaussian integral. So what you do is that you take, so it's valid in any dimension. You are in a bounded domain G, and you look at a Gaussian field, Gaussian distribution, with which is correlated with a log. Okay. So then you regularize your field with any reasonable regularization, so that the log is truncated. So you can regularize the log this way. I mean, your field, once regularized, it should have a covariance given by this kernel here. And the Sine-Gordon transformation, this is an exact relation that expresses the partition function of the two-component plasma in terms of this integral here. So here this is the expectation with respect to your field here. So you have an interaction term, which is the cosine of the Gaussian fields. Okay, and the question is, can you pass to the limit when the scale, well, the parameter, the cutoff parameter t is sent to infinity? Okay.
Should be EDZ, I guess, right? In the measure, the Lebesgue measure.
Yes, it's a DZ. It's well, because I'm focused on dimension. But no, okay, it's a DZ. Yes, it's a DZ. It's a Lebesgue measure over the domain. Okay, so this is the Sine-Gordon transformation, and this is an exact relation. And well, one way of studying the two-component plasma is to pass to the limit in this model. Okay. So, well, this model has been studied. Well, there is a whole literature on this model. It's mostly studied in 2D because of the relation you mentioned with the neutral 2D Coulomb gas. So, well, the multiple picture first appeared in a paper by Froelich, and it also shows that the model converges in the first region of the parameters. Well, it was in dimension 2, but I guess well, to stick to my notation, I keep the dimension d here. It's in a general level. So there. Then the successive thresholds have been studied by a lot of people, among which David here. And so the convergence of this partition function. So as I said, because of the multiple picture, you expect that you have to regulate your partition function with counter terms to control the divergences occurring from two peoples. And this has been done at first place for small n. And the paper of David and Kennedy is the first I saw that which treats a bit the correlation functions. So this is not the correlation function that I'm interested in, but this is the only paper I've seen where correlation functions are indeed treated. Okay. Then, when you want to treat all the thresholds, there are a bunch of papers, but they only give bounds on the partition function. They do not control they do not show the convergence of the partition function. And then there are other papers on the topic that are not connected, related to my talk, but I mentioned all the same. So there are a few papers about the Cathy transition by Falco, Fröhlich, and Spencer. There's been a paper recently on large deviation for a discretized version of this model by Leblé, Serfati, and Zaitouni, with a contribution of Wu. And more recently, there's been an approach of this model by the dynamical Sine-Gordon model, so by Aochen here and Martin and Ajay Kandra. So basically, you construct dynamics for which the invariant measure is given by the model I'm studying here. Okay. So in all these papers, so there are some restrictions in the papers, and maybe we can discuss just a bit, and you can correct me if I'm wrong, but here mostly this model is studied from the angle of the RG flow. So it may happen, for instance, in the paper by Jimock and Hurd, that you have restriction on the constant here, on the constant alpha. This model is also mostly studied for the Yukawa gas. It's not exactly the Coulomb, the 2D Coulomb gas. It's the Yukawa gas, because my guess is that for the Yukawa gas the RG map is more easily defined. But okay, there are a few restrictions, and well, the conclusion of all that is that there is a whole literature on the model. The model is more or less understood, but if you want to go into technical details, it's not clear that we can treat entirely this model. Okay, so I just want to present another approach which doesn't rely on the RG map to try to do something with this model. Okay, so I will focus on the 1D Sine-Gordon model. So you take here I take the dimension equal to 1, and I take a bounded interval on the real line, and I take so my cutoff process will be Gaussian, but it's a martingale cutoff. I mean, you take a family of Gaussian fields whose correlation are given by this integral here. So if you want, so the t parameter here stands for the cutoff of my Gaussian field. So when you send the t to infinity, the covariance is given by the integral here between 0 and infinity, and you ask for this total covariance to be a log. Okay, whatever the big O term behind the log, you can take it to 0 if you want. Okay, and you assume a bit of regularity on the Q, but well, this is more or less what you want, is that this process, this Gaussian process here, is a regularization of a log correlated field on the real line. Okay, and the question is, study the limit of the, well, I mean the partition function of the Sine-Gordon model in 1D. Okay, so you can, if you can do so, you can study the Sine-Gordon model on the boundary Sine-Gordon model I showed you in the paper by Fadeyev, Zamolodchikov brothers, and stuff like that. And Lukianov, yes?
What is the dependence in U of QU?
Sorry, U is the contribution at scale U of your kernel. So basically what you can have in mind is that for Gaussian free fields, what is this QU here? For Gaussian free fields, the QU of xy is basically something like that. Is exponential minus 2u x minus y squared. Okay, so this is the contribution. It's like if you have a Gaussian measure, which is with independent increments, and the contribution of increments at scale u is given by this Gaussian kernel here. Okay, so if you want to treat phi fields, basically you have to consider this kernel here. So I want to explain how to pass to the limit in this partition function, and eventually in the second part of my talk to treat the limit when you consider correlation functions. Okay, so this is once again, well, as I said, this Sine-Gordon threshold do not depend on the dimension. So you define as for any dimension, you define the successive threshold in this model. So in dimension d, you just have 2 times d instead of 2. but here, so as g is equal to 1, you have this sequence of thresholds, and you consider the martingale, which is given by the cos, and which is Vic ordered. Okay, and you denote by ck of t the case cumulant of this martingale, and turns out that, well, this is known since the first paper on Sine-Gordon, that if you want to establish the limit of the convergence of the partition function, you have to subtract counter terms to this partition function. The counter terms are given by the cumulants of your martingale, and the number of cumulants you have to take depends on the region where your parameter beta is located between the thresholds. Okay. So if you so this is a statement that is well understood. At least, yes. Well, this is well understood, and furthermore, you can show the convergence of this partition function evaluated at arbitrary functionals when the parameter t is sent to infinity. Here, let me just say, I don't want to discuss that much here what is the f here, but let's say that it is a gentle f. This is not the type of correlation function I have discussed in the beginning of my talk. This is a gentle f, but you can take the limit here, so that you can define a probability measure on the space of continuous function with the Sine-Gordon model. So this is the first theorem, and this is, I will explain in the second part of my talk the proof of this statement. And the second thing we are able to prove, we don't know, so this theorem, as I said, is well known and is probably optimal. It is optimal, it's known. But now I want to discuss correlation function, and I'm not sure to which extent this theorem is optimal. At least it will show that we can define correlation functions, non-trivial correlation function of the model for any value of beta until the optimal values of beta. So what you are interested now is, well, I'm interested in the correlation function of charge densities. These are these exponential terms here. And I want to discuss the existence of this limit here, which is the partition function of the Sine-Gordon model evaluated at this special functional here, which is actually, it's rather singular here because you have an exponential of the field. You know that the limiting field has a log kernel, so it's not a fairly defined function. So it's not clear that this limit is well defined. I mean, a priori, it's not clear that this limit exists. So the statement is that first, you can consider an arbitrary number of correlation charge correlations. Each charge correlation depends on the parameter, which let's call it eta k, and it modifies the Sine-Gordon threshold. So here you take the maximum of the eta k, and the two that here you have the two that comes from the convergence of the partition function, but you have to tame it by 1 minus the maximum of these charges. So it modifies clearly the Sine-Gordon threshold, but well, if beta squared is less than 2 times this term here, you can show that for beta belonging to the correct region of parameters, this correlation functions are well defined, meaning that you can find the limit for these quantities here. So this defines in some way the correlation function of the 1D plasma, well, infinite volume. So concerning your question, this is the finite volume limit in the Sine-Gordon model. In the beginning, the correlation functions given by FADF, and it's about the infinite volume limit. First, you UV regularize, then you take the limit when the domain goes to the real line, and the formula I show you in the first slide is about this correlation function defined on the wall line. Okay, so you have an existence, non-trivial existence of correlation function for this model, and what I want to explain is the proof of this result, because it does not rely on the RG map. So basically we need the 3 ingredients. So the first is a probabilistic representation for the cumulants of a martingale. Then an argument of concentration for martingales, and to have concentration, we need an inequality of type Onsager. So let me illustrate these points first for the concentration of martingales. So you can treat just with a simple argument the first phase of the model, and this works in any dimension. So you look at your martingale here, and if you want to define in the first region of the model, if you want to define the Sine-Gordon model, you have to show that this martingale converges when t goes to infinity, and that it possesses exponential moments. Okay, how do you do that? So you just compute the bracket, and the bracket is, well, it's a simple exercise to see that the bracket is given by this quantity here. Here you have the product of two terms, which are sine.
Not an expectation, it's a quadratic variation.
Yeah, I said expectation. No, it's quadratic variation. So it's a bracket. Compute the bracket, and the bracket, it's easy to see that it's given by this quantity here. So you have two sinus here, two sine here. So these are clearly terms that are bounded, and you have this quantity here. So basically, the approximation you can make is that, okay, Q of R, the contribution of the correlation at scale R, it's more or less looks like that. And the good approximation, well, take your Gaussian if you want. A good approximation, you can say, okay, your Gaussian kernel looks like that. You can just say that it's an indicator function, okay? It works the same. So you just replace your Q here by indicator function. And so this tells you that, sorry, it tells you that here you just, if you make this replacement, tells you that you just have to integrate between 0 and the log here of this exponential term here. But here you can just estimate you can just make a very crude estimate. This quantity here is bounded by this quantity here. So it's finite for beta square less than 1. Okay, but there is a theorem in a martingale theory that tells you that if the brackets of a martingale are bounded by a deterministic quantity, then you have concentration for this martingale. This is a result by Azuma and York. Tells you that actually your limiting martingale has exponential tail. Okay, so if it has exponential tails, it's clear that this expectation is finite. Okay, and this will give you automatically the convergence of what is called the Maillard expansion in the literature. Okay, this implies the convergence of Maillard expansion. So this, with a simple argument of concentration for martingales, you can show the convergence of the Sine-Gordon model in the first region. Yeah. Okay, questions? Okay, so now how do you proceed in higher thresholds? So first, let me recall the definition of cumulants. So if you take a bounded martingale, if you look at this expectation here, well, it's not difficult to see that this quantity here should be analytic in alpha. So you can start with a non-trivial radius of convergence, and you can certainly expand this function here around 0. And the successive term in the expansion are the cumulants of the martingale. Okay. So if you want to give a probabilistic representation to these cumulants, what you do is the following. First you consider, you construct recursively a sequence of martingales that will give you a representation for your cumulants. So the way you do that is the first martingale you consider is your martingale. Okay, so the first martingale is your martingale, the cosine martingale minus its value at time 0. And then when you are at step I, you sum all the brackets of the martingale you have already constructed, whose index sum up to j, sorry. And so you make these sums. Eventually you can compute this quantity. It's not the point here, but you can construct, clearly you can construct iteratively this sequence of martingales. You compute the brackets, and this gives you a quantity that I call A, and the martingale at time j is just the expectation, the conditional expectation of your process here, conditionally on all the values of the field up to time s, okay, minus its mean. So you can construct, well, you can construct iterate inductively this sequence of martingales. And the thing is that if you look at the expectation, so this is the partition function of the Sine-Gordon model.
Sorry.
Yes.
You have an S here and you MS, J, T.
Yes. So
In the bracket you don't have that.
so you are at time t.
Oh, that is time T.
You are at time t, but when you fix the time, you can construct a martingale which depends on t, but the parameter of the martingale is S. Okay, and you can construct this martingale by conditioning this sum of brackets by the expectation by the sigma algebra generated by the cutoff field up to time S. Okay, this will give you a martingale. Okay, and the thing is that if you look at the partition function of the Sine-Gordon model tamed by the successive cumulants, it has a representation in terms of martingale. The martingale here, here the n is a martingale which is the sum of all the martingales you've constructed up to time n, and with a rest, and this rest is just a sum of brackets for with sum of index bigger than n plus 1. So this is maybe not very maybe does not ring a bell to you because it's just a complicated formula, but if you well, actually it's not difficult to convince oneself that it's a natural procedure to give a representation for the cumulants, and the GS cumulant is just the expectation value of this process here. Okay, so now if you want to make to prove that this guy converge, you just have to study this guy here, exponential of q, under this new probability measure, because here you have a martingale minus its 1/2 of this bracket. So this defines a new probability measure, and you can look at the convergence of this guy here by looking at this process here. So this is the first step of the proof. You have a nice probabilistic representation for the partition function renormalized by the cumulants. Okay, so now you have to deal with brackets of martingales, and in the case where this is the cosine, my statement was general in the slide before, but if you take the cosine martingale, you can, well, you have exactly the same statement, and so if you want to show that this guy converge, you have to control brackets, because you have here a martingale minus its bracket, and the q term, the rest, if you want, is just a sum of brackets. So if you want to say something about this expectation here, you have to be able to say something about this sum of brackets here, and this is what I want to explain. Okay. So how do you?
In a way, it's just a generalization of the exponential martingale formula, right?
Yes. Well, just yes. This is the most well. Well, the most intuitive generalization you can make of the argument for the first threshold. Okay. Okay. So the thing is that you can actually find a form for this bracket. If you compute the brackets of two martingales whose indexes sum up to j, actually you can see that this bracket takes this form. Here you have a cosine. This is a sum. Here you have a sum of lambda k, which are just well, which stands, if you want, for the charges of your particles located at xk. So the lambda k takes the value plus or minus 1, and here you have a function. Let's call it fj, and the estimate you want to prove is that this fj satisfies this inequality here. And why is it enough for what we want? Well, let's find a bound for this quantity here, admitting that this is true. Okay, so you can, if you look at this integral, so we have an integral over I to the power g. So exponential of u times the cos. So the cos here doesn't matter. You can bound it by 1. So you just have to compute this quantity here. And assuming that this bound is true, this will give you an integral which looks like that. So here I can replace it by this term here, plus beta squared IU du. Okay? So when does this integral converge? You see that this guy has to be greater than minus this one. So it converges provided that beta squared over 2 I less than j minus 1. Okay? This is exactly the condition I told you. This is equivalent to beta squared less than 2 1 minus 1 over j. Okay? So these integrals here, the integral that you got here, are bounded provided that beta squared is less than 2 1 minus 1 over j. And this is exactly the condition for the thresholds. Okay? So here you see that where this condition for thresholds comes. And how, so how can you prove such a bound? You can prove it by induction, and for the induction to be true, you need some way of recovering the function fg from lower index. So there is a fusion rule if you want. So you can find a function f for the index g plus g prime by fusing terms coming from lower index, say, let's call it j and g prime. Okay, the fusion rule. Well, there is an explicit formula which looks like that. So how do you fuse two terms? Here you have first terms coming which is lambda k. Here you have another term coming from with its own lambda k. So the one here means that it comes from this first term here, and the 2 means that the lambda k comes from this term here. Well, actually it's not very important because I won't explain how you do the induction here, but let's say that once you are given fj and fj prime, you can recover the fj plus g prime by fusing the terms, and the terms are to be tamed by this energy term here, and this energy term is the sum of the sine times the kernel. Okay, so if you, it's not difficult to see that if you want to show by induction that this new function here satisfies a bound of this type, you have to be able to control this term from below by this quantity here. Okay, and the minus 1 that you've got here is very important to get exactly the one that you've got here. Okay, and this type of inequalities are called Onsager inequalities in the literature. And now what I want to show is how you can prove a modified version of Onsager inequalities, which is the inequality here in red. Okay, so provided that Onsager is true, you can show that inductively you have a bound for the brackets of the martingale. The bound is here, and how can you hope to prove this bound by induction? This is because of this fusion rule or fusing rule, if you want. Okay, so how do you prove this Onsager-like inequalities? So let me recall first Onsager. What is the Onsager inequality? Let me simplify a bit the framework. Let's take Q here just equal to some function of, well, let me take the simple situation where the Q is given by some given function Q to this exponential term here. So for instance, Q can be exactly the Gaussian kernel. Okay, so take a configuration of n charges which are in your interval. It's charge, well, you don't necessarily assume that this configuration of charge is neutral, and you define the sum, this sum here, okay, the sum of all the product of charges times the kernel. Well, Onsager, in this context, Onsager inequality tells you that this quantity u here, this energy, is bounded from below by minus nt. Okay, and the proof is rather well, it's rather simple. Here you have a sum over all non-diagonal terms here. Okay, so you can certainly rewrite this sum here by the sum over all terms including diagonal, minus the diagonal terms. Okay, the sum over non-diagonal terms, it's a sum over all terms minus the diagonal. And here, as you have a kernel which is a positive definite, this quantity is certainly positive. Okay, because Q is positive definite. Okay, so this quantity is positive. So the whole sum here is bigger than this term, and this term, when you are at when the points are equal, this Q here is equal to 0, to 1, sorry. So this Q here is equal to 1, so you integrate between 0 and t, this gives you t, so you have minus nt here, okay. This is Onsager inequalities, and if you want to get the minus 1, here you don't have the minus 1 I need, okay. If you want the minus 1 here, you need to be a bit more efficient when estimating this term here, okay. Here, I estimate this term by 0, I get Onsager. I want to estimate this term by t, okay, to gain the 1. So how do you do that? Let me show you, it takes one slide to explain how it works. So assume you are given, in the case where you have an equal number of plus and minus charge, let me introduce the dipole distance. So the definition of this dipole distance is this quantity here. Here, this is just the group of permutation of n over 2 elements, but it's better understood on a picture. So you have an even number of charges. You have the same amount of positive and negative charges, and you pair all the plus with a minus. Okay, so you can do that, for instance. This is a possible pairing. Okay. When you have just such a pairing, you compute the total length, the sum of all the black rows in my graph. Okay, so you compute the total sum of all these lengths. This gives you one possible sum here. But obviously, this is not the best choice you can make. This is certainly the optimal pairings. Okay, so if you group your minus and plus this way, you obtain the optimal pairing, and the dipole distance is this sum here, this distance plus this one, plus this one, plus this one. Okay? So this is what I call the dipole distance. So now take n charges, not necessarily neutral. I want to estimate this energy term here, and the claim is that if n is even and you have a neutral configuration of charges, then the energy term is bigger than the quantity you want up to the log of the dipole distance. And in all other cases, you can gain the 1 here, okay, without any additional term. This is what I want to show you. You are still not 10 minutes, or just only one slide left. I can take my time. Any question? No? Okay. So I want to show you how you can gain this one. This is just an argument we can understand on a few pictures. So we take a configuration of charges, n charges, as in my previous slide, and I want to partition the charges into a group of disjoint indices. So here you have different groups, and I want that each group, the diameter here is less than the cutoff scale. Okay, I want that each group is less than exponential of minus r, and the distance between two groups is bigger than exponential of minus r. Okay, so I want to partition the space this way. So of course, you will tell me it's not always possible to have such a partition. Okay, for instance, if you have this configuration, okay, you have here a small distance here, very small, but when you look at the whole configuration, you cannot split into a separate cluster of charges. Okay, so I want to separate my particles into disjoint clusters like here, but it's not always possible. How can you make sure that it is possible? Actually, a sufficient condition for such a partition to exist is that all the charges, the location of charge, are either less this distance here, you can record that either this distance is less than 1 over n, number of particles, or it is bigger than 1. How do you do that? How can you see that? Sorry. That for a given index, so maybe with a picture, since we have time.
Do you require each group has a 1 or minus 1 or 0
Sorry?
for the charge? When you do the partition, do you require each group has either 0, 1, minus 1, or it can be?
No. The sum of charges? No. I don't care about, for the time being, I don't care about the charge I have inside each cluster. I just want to partition. It's just about, here it's just about location in the space, okay? I want to have separate cluster, and so if you choose any index, you say that if you take a particle, you say that each particle which satisfies this distance is less than 1 over n will be in the same cluster. So for this particle here, let's call it K, I put in my I put around it all the particles, all the index which satisfies this inequality here less than 1 over n, okay? And all other particles which satisfies bigger than 1 won't be in the same cluster, okay? So in the end, when you have gathered all the particles, what do you have? If you want to compute the diameter of what you have, here this is less than 1 over n times the scale. Here the same, and so by the triangular inequalities, the total distance between two possible particles here is less than the number of particles times this exponential divided by n, but the number of particles is less than n, so this is less than exponential of minus r. So if you have such a condition here, you can partition your configuration into clusters which are far away from each other, okay? So in this, and furthermore, this condition here tells you that if you look at the scales for which the partition function does not exist, it has a bounded Lebesgue measure. So it means that for almost all the scale, you have a partition function of configuration. You have a partition of your configuration. Okay, so now the thing is that, so now you have your configuration in two separate clusters. Well, more or less you can justify the following approximation. You can consider that two separate clusters do not interact, okay? And particles in the same cluster are considered to be the same, okay? So this sum here, you can certainly, this integral here, you can restrict integration over time for which the partition exists, okay, the partition into clusters. Once you have partition into clusters, you say that, well, separate clusters do not interact, so you can separate this sum here into the sum over separate clusters, and inside each cluster, you can consider that these two guys are the same, so this Q becomes 1. So inside each cluster, you have just the sum, the contribution is just the sum of charges to the square, okay? Because in each cluster, you can consider that the positions are equal, and when the positions are equal, the Q is equal to 1. Okay, so
It's a bound or
this is a lower bound.
not an idea.
Yes, this is a greater or equal to, yes, sorry. So in the end, you have this a lower band which is given by that. And so now the question is there a cluster for which the sum of charge is not 0? Okay? Because if one of the cluster has a total sum of charge which is not 0, this quantity is bigger than T. Okay? So obviously, if the total sum of all the charges is not 0, you are stuck to finding one of the cluster for which the sum is not equal to 0. Okay? Because otherwise, if all clusters sum up to 0, the total sum must be 0. Okay? So if the sum of the charge is not 0, then one of these clusters does not sum to 0, and so when it's an integer, it's at least 1. And when you squared, again 1, and you integrate over time, you get your lower bound by t. Okay. Now the interesting case is when the sum of charge is equal to 0. Then there will be scales. If the scale R is large enough, I mean, you can even quantify large enough precisely what you mean. If the scale is smaller than the dipole distance, then you necessarily have to find a group, a cluster, for which the sum of charge is not 0. And the argument is that assume by contradiction that well, this is satisfied, but there is all the group have a 0 sign. So inside each cluster, you can. This means that you have the same amount of plus and minus inside each cluster. So you can pair all the charge into dipoles inside each cluster, and this gives you that the dipole distance. You can evaluate the dipole distance with your pairing, and your pairing tells you that the dipole distance has to be less than the number of dipoles, so n over 2 times the diameter of each cluster, which is exponential of minus r. Okay, so this is a contradiction because you have assumed that this is not true. Okay, so just to yes, okay. Sorry, so just well, so maybe I don't know if this last argument is clear, but I'm just saying that assume that assume that in each cluster the sum of charges is 0. Okay, so if this is true, you have your clusters. You have here, say, 2 particles here. Okay, assume that your configuration is like that. So the sum in each cluster is 0. So you can have a pairing here. You can pair these 2 particles here. Here you can pair these particles here. And if you look at the dipole distance that you've created, this is here each diameter is less than exponential of minus r. So you have a pairing for which the sum of lengths is less than sum of each distance here, so exponential minus r, times the number of dipoles you have created. So 1, 2, 3, 6. Okay, so times number of dipoles. Okay, and the number of dipoles is the number of particles divided by 2. Okay, so if all the clusters sum up to 0, then this condition cannot be true. Okay, so that if R is large enough so that this condition is realized, then you have necessarily one of the clusters which has more plus or more sign than, and so one of these sum here is non-zero, and so this integral is bigger than t. So this completes the proof, more or less. Okay, I'm done.
Why did you say this is not an RG map? It looks like RG, in fact. The method that you explained, where you have x of t, so it's like you have a random field in space plus an extra scale dimension, and you're kind of looking at the boundary values at t equal infinity. It looks a lot like the French approach to the RG.
Yeah, okay. Well, it looks like we can quantify or not, but okay, if you want. The thing is that in the end, well, it's not clear because because of several reasons, but the method is very flexible. I mean, like, here I just explained the proof for the partition function, but you can plug any background measure for the cosine term. What I mean is that you can study the Sine-Gordon model where you have an exponential of cos beta x mu gx with mu very bad, if you want, a background measure which is very bad, and it will tell you exactly, depending on the structure of mu, what will be the sequence of threshold you see. So this is the kind of proof we wanted, because the correlation functions amounts to changing the background measure, and so we wanted to see explicitly the dependence of the threshold on the background measure. Okay. For the RG map, as far as I understand, the thing is that the RG flow is most easily studied when things are well, say homogeneous in space. Well, okay, and so this is my guess is that this is why these people looking at the RG flow look at the Yukawa gas, for which it's more easier to define and see the RG map because it's translation invariant. This is why they do not look at correlation functions, because when you perturb the mu here, this creates very strong, this breaks very strongly translational invariance. And also I guess this is why David maybe and Kennedy are the only papers I found treating correlation functions, because they use Hamilton-Jacobi solutions for which the RG map is not used. So it's not exactly the RG map. So this is why the method, and our method, I would say, is more close to that of to the method by David and Kennedy. I'm not sure that. Well, if I want to compare this method to somebody here, it's more David's method.
Yeah, but there is this other approach by the group in Paris, Feldman, Magnani, Vassou, and Senior, where you work.
Who's that?
By Feldman, Magnani, Vassou, and Senior, there is this where you decompose your field in phase space. So you have, you can see it as a random field in a space which has an extra dimension, where the extra dimension is the scale. It looks a lot like how you started defining.
Yeah, sure. But I mean, my guess is that whatever the approach, you have to decompose into scales. Yes, and then you treat as you can. But the scale, I mean, the skeleton of every proof of the Sine-Gordon is the decomposition into scales, I guess.
By the way, are you aware there is a work by Unila and Saxman?
Yes.
That they look at the pure imaginary VFX and the Sine-Gordon model. So how does it compare with you?
I wouldn't say that they look at the Sine-Gordon. They look at the Onsager inequalities.
Yes, they do have.
Yes, and this is exactly the well.
They have a number of Onsager inequalities.
Yes, and the Onsager inequality I showed you, the first one I showed you, this is the same as their proof. The one-line proof is their proof. But I'm not sure that well, I wouldn't say that the focus of their paper was to study Sine-Gordon. The result that they have a nice decomposition of Gaussian processes that allows them to prove results very easily, and among their application is the Onsager inequality.
They also have something about Sine-Gordon, if I remember correctly.
No, the moments of on the moments, and the techniques to estimate moments is with the Onsager inequalities is the same as you can find the paper by Zaitouni, Serfati and Leblay. More or less, it's they extend their argument.
So what about two dimensions?
Two dimension. The problem there is something in the proof, and the problem is not really the dimension. Is the regularity of the cutoff of the cutoff process at the scale of the cutoff. For instance, if the cutoff is very nice, let's say hierarchical, we can prove the proof takes if you takes 3 pages in any dimension, but for the hierarchical model the cutoff is very nice. Okay, if we don't have well, depending on the dimension, we are able to treat almost all Gaussian processes. I can mention one, but then if dimension increases, this restricts the type of cutoff we can use. So still we are thinking of improving the method to be very general at every level. But for instance, we are very general at level 1. In dimension 2, 3, whatever you want, well, let's just say that the model we can very easily treat is the hierarchical model, whatever the dimension. You can construct the hierarchical model in any dimension, okay? So we have still a problem to handle something technically in any dimension.
Last question, quick.
In the hierarchical model, I mean, what you explained at the end with the clustering, the problem disappears completely, right?
Yes.
Is there other simplifications than that?
The structure of the cumulants are way simpler. Yes, you're right. Everything is well. Everything is so simple with the hierarchical model that I don't even want to explain. You can renormalize everything you want with the hierarchical, and it's not difficult in any dimension. You're right.
Good subject for the coffee. Thank you again.